Jewish postdoc, everyone, Robert.
Hi, everyone.
All right, and he's going to tell us today about PRGs in VNC 0, which you know some of the words.
Yeah. So thanks everyone for coming. I think I've met most of you, but it's just, hi, I'm here. So I want to tell you about, I guess this talk has two purposes. So one is just to tell you about something that I've been thinking about recently that I think is cool, but also give you an idea of, what are the sorts of problems that I like to work on? What do I like thinking about? What am I doing? What's this guy who's sitting in the office, like, what's he actually doing? So like Sapir said, this is about some kind of pseudorandomness in NC0, but it's like an algebraic kind of pseudorandomness. And because we're talking about algebraic complexity classes, there's always this V in the front of the class name, which is for valiant. But if you know what NC0 is, this is just NC0. Otherwise, it'll become apparent as the talk progresses. Okay, so what are we talking about? This is algebraic complexity, which I know is like super popular here. Everyone works on it. But I just want to make sure we're all on the same page with respect to the model. In this talk, we're going to look at algebraic circuits. So these are like Boolean circuits, but they're algebraic. They're built out of addition and multiplication gates. They take as input formal variables, and they output a polynomial. So for example, this circuit here, it takes two variables x and y as input. It does some computation, and then it outputs the polynomial x squared minus y squared. As far as parameters of these circuits, we'll be concerned with their size, which is the number of wires in the circuit, and also their depth, which is the length of the longest path from an input to an output. I'll be talking about low depth circuits, so I'm okay with unbounded fan-in. You can also restrict these to have fan-in too if you like. So these are the things that we want to look at as far as computation is concerned. Now, one of my favorite problems that has to do with algebraic circuits is this polynomial identity testing problem. So what is the problem? I give you as input a multivariate polynomial, and I'm giving it to you as an algebraic circuit. And your job is to decide, does this polynomial equal this identically zero polynomial? Now, how would you solve this? One thing you can do is you can always take the circuit, open up all the parentheses, check if all the monomials cancel. And this gives you an algorithm, but it's something like an exponential time algorithm. You can actually do much better if you allow yourself the use of randomness. So you can solve this problem efficiently with randomness, in fact, just by evaluating the circuit at a randomly chosen point from a large grid. And the Schwartz-Zippel lemma will tell you that if you do this evaluation, well, if f is 0, you always see 0. And if f is non-zero, you see a non-zero evaluation about half the time, at least half the time. And so this gives you an efficient randomized algorithm. And this is a really nice problem. I like it because I like algebra. But of course, only 99% of the people in this room like algebra. There's that 1% who doesn't. So if you'd like to work on other things, there are other reasons that you might care about this problem. For example, it has applications that go far beyond just things that look algebraic on their face. So for example, using identity testing, you can design parallel algorithms for combinatorial optimization problems like perfect matching. You can, of course, use this, this identity testing perspective. It was useful in this deterministic polynomial-time primality testing algorithm of Algorithmic, Kyle, and Saxena. So we're going from algebra to number theory. That's not such a big jump, but it's still a jump. And of course, you can use identity testing in problems related to polynomials and algebra. So it's a widely applicable problem. And in fact, it sort of captures like an algebraic fragment of the P versus BPP problem. We have an efficient randomized algorithm, and we're really interested in designing an efficient deterministic algorithm. And of course, you could say, well, like, this is just one problem. Why should I care about this problem in particular? It turns out that derandomizing PIT, it has really interesting circuit lower bounds consequences, but it's empirically complete for like algebraic co-RP, in the sense that if you have an algebraic algorithm and it uses randomness, almost all the time, the reason for that randomness is because you're solving instances of PIT. So, even if this isn't complete in a formal sense for some class of computation, it captures a lot of things we like to do. So we might as well try to design a deterministic algorithm. So let me tell you how these algorithms typically are designed. And usually these algorithms proceed by constructing a pseudorandom object called a heading set generator. So let me explain what these objects are. So in in this definition, we have some set of polynomials curly C that we're interested in testing. So you should think of curly C as being all the polynomials that are computable by small circuits or small formulas, something, some computational bound is implied. So what we're interested in are maps curly G that take L variables to N variables. Each output is going to be some polynomial function of the inputs. And we're going to say that this map curly G is a hitting set generator for curly C if the following property holds. For every F in curly C, every polynomial we're interested in testing, F is identically 0 exactly when the composition of F and this generator is also identically 0. So this gives you a reduction that says if I want to test F, it suffices and is correct to test F composed with G. Okay, now there are two parameters of this generator that we'll care about. The seed length, which is the input, number of inputs to the generator. Here it's this L. We'll also care about the degree of the generator, which is the maximum over the degrees of these output functions. And we'll also care about the complexity of actually evaluating the generator. Given an input, output one of the coordinates or all of the coordinates of the generator. So those are the different things we'll care about. Now, why does designing one of these generators actually give you an algorithm for PIT?
So, yeah. I think I'm having a hard time parsing the notation.
Yeah.
So here, what is G mapping what to what?
So you can think of it as two different ways. So G just maps a vector of complex numbers to another vector of complex numbers, okay, where each output is described, it's describable as a polynomial function of the inputs, or it's just a vector of polynomials. And we're going to do this substitution of polynomials into some circuit that we're going to test.
Conspicuous by its absence is any comment about the degree of those polynomials.
Right, so that's one parameter of the generator that we'll measure.
Oh, okay. Oh, yeah. I should read the bottom line. Yeah.
No, I was standing in front of it. Does that...
So as a pure G, why are like your first the seed random bits, and then G is stretching them, and that's the one you're feeding F?
Yes. So that's one perspective, is that you're taking L truly random, say, complex numbers to N pseudo-random complex numbers. You can think of bits, but,
sure.
Yes. Good. Yes. Other questions? Okay. So how do you use these things to actually design algorithms? So I claim that if you have some set of polynomials you want to test, and you have a generator, this gives you a faster deterministic algorithm to test those polynomials. So, what can you do? I mean, one algorithm is just the stupid brute force algorithm. You take your polynomial, and you test if it's 0 by brute force. You evaluate it on so many points that you can just interpolate back the coefficients and see, is this polynomial 0 or non-zero? This needs an absurdly large number of evaluations. You need something like degree plus 1 raised to n the number of variables, many evaluations to perform this test. So this is an exponential time algorithm, it's deterministic. But if we have a generator, we can look at a different algorithm. You can say, instead, I'm going to first compose F with the generator G, and now I'll test if the composition is 0, again by brute force. And now here, the running time, it has the same flavor. It's degree, now here the degrees multiply, and it's raised to the number of variables, which is the seed length L of the generator. Now, this algorithm is correct because the definition of a generator is tailored to make this algorithm correct. Now, if you get a generator that has a small seed length compared to n, right? If L is small compared to n, the degree is not too large, and say the generator can also be evaluated efficiently, then you've got an improved deterministic algorithm. Okay, so typically, the focus is going to be on improving the seed length of the generator while keeping the other parameters reasonable. We'll focus on something else in this talk. So let me tell you,
Sorry, here, if this is, let's say this was your only application, then you are asking way too much. No, you want to say that one of the y's will give you 0, but now you are saying every time What was the definition of the generator again?
So if f was the identically zero polynomial,
Yes.
then of course the composition remains identically zero.
Yes.
And the definition of a generator says that if this composition is identically zero, then f must have been zero to begin with. That's the only way you get identically zero here. Right. So it just says this reduction is correct. Okay. So broad strokes, how would you go about designing one of these objects? Well, there are sort of two regimes that tend to appear in algebraic pseudorandomness. One is where you're working with a very weak circuit class. And here I just have some names of these things if you know what they are. That's great. If you don't, you should just think of these as, these are weak enough circuit classes that we can prove exponential lower bounds. We can really get our hands on these circuits and understand what they're doing. So how would you design a generator? Well, the first step is you're going to work really hard to understand what these circuits are doing and understand why they're weak in some way or another. And then once you've done that, you use the intuition and the knowledge you've gained from, say, proving a lower bound to go and design a generator. This is extremely vague and hand-wavy. You're not really meant to learn something from this. This is just to say this is one sort of way that people design generators in practice. The other sort of regime is where you're working with strong circuit classes, like unrestricted circuits or maybe formulas. These are strong kinds of circuits where we can't prove lower bounds yet. Or if we can prove lower bounds, they're pretty weak, pretty mild. We don't understand really these kinds of computation left yet. Even low depth circuits in algebraic complexity are surprisingly strong and surprisingly not well understood. So what do you do here to design a generator? Well, instead you work really hard to develop some kind of hardness versus randomness machinery. You develop some kind of theorem that says if you can prove a lower bound, then you can use this for derandomization. You can use a lower bound to design a generator. And then you just have to prove lower bounds for a hard function like the permanent. So, the kinds of generators that I want to tell you about in this talk, they're really going to fit in this second regime, where we're doing something like hardness versus randomness. We're taking a lower bound and we're upgrading it sort of in a proof agnostic way into a generator. So we know there's a lower bound. We don't know how it was proven. Typically here you need to know how the lower bound was proven. You make use of that. We just have a lower bound. Let's upgrade it to a generator. Okay. So typically, like I said, the goal is to minimize the seed length and keep the other parameters reasonable. Keep the degree reasonable, keep the complexity of the generator reasonable. And this is what you need to do for derandomization applications.
So why did you say you upgrade it to a generator? So a generator is a stronger object than a lower bound?
Yes, because if I have a generator, I can always interpolate a polynomial that will vanish when it's composed with the generator. And because of the generator property, this polynomial gets some kind of lower bound. I'll come back to this in a few slides and it should make sense, but generators are generally stronger than a lower bound. They imply lower bounds. Okay, so typical parameters, minimize seed length, keep everything else reasonable. That's what you need for derandomization applications. In this talk, I want to focus on the parameters in a different order of importance. I want to minimize the complexity of the generator, make it as small as possible, as simple as possible to compute, and just keep the other parameters non-trivial. That's the goal. And you can ask well, why? Why should you care about this? Because this is not going to give you good derandomization. This is like some other task. And I have a few answers. One is just, I think this is like a totally natural question, and it's relatively unexplored as far as algebraic pseudorandomness is concerned. This is really a question that's only popped up in the past couple of years. We don't know much about this. It also turns out that this question has answers, and it has interesting answers in Boolean pseudorandomness and in cryptography. We know that under reasonable assumptions, you have objects like one-way functions and pseudorandom generators that are computable in what's called NC0, where every output bit just depends on a constant number of input bits. And not only are those results interesting, but the techniques have further applications. So by analogy, answering this question in the algebraic setting should maybe give us interesting answers or interesting techniques. And then it's also connected to some outstanding open problems in algebraic proof complexity. If there's time at the end, I'll tell you a little bit about what that connection is. And it's also connected to this, sort of ongoing work on this algebraic natural proofs barrier, which is, if you don't know what natural proofs are, there's this wonderful paper by Razborov and Rudich from the 90s that, basically the message is, here's some formal thing called a natural proof. It captures all the circuit lower bounds we've seen up until the mid-90s. And if you believe cryptography exists, natural proofs can't prove circuit lower bounds. You can only prove lower bounds for restricted classes. So this gives you a really good excuse for not having proven P not equal to NP. And in algebra, we're also looking for this excuse. Why can't we prove circuit lower bounds? There's some version of algebraic natural proofs, but we don't know if there's a barrier there yet. And so constructing these really low complexity generators, it has some connections to understanding if there's this natural proofs barrier or not. So I won't talk about this. Maybe I'll talk about the proof complexity at the end if there's time. But I will just assert that this is a natural question and you're all stuck in this room and it's impolite to leave now. So going on, I want to tell you, what is the sort of thing that we're getting. And I think a really nice example for understanding, existing work on pseudorandomness and the new thing is to look at low depth circuits. Because here we have unconditional constructions. I've already defined circuits in depth. You know what a low depth circuit is. I don't need to introduce assumptions or new definitions. So I want to tell you what we know about generators that hit circuits of some depth delta. You should think of delta as a large constant, like 1,000, and polynomial size. So there are 3 generators. I'm going to tell you their parameters. And we're going to compare, how they differ in terms of seed length, their degree, and then the complexity of actually evaluating an output of the generator. Yes?
Are the lower bounds here in algebraic circuit also similar to boolean, like 2 to the n to the 1 over delta? Or?
Good question. They're not. They're extremely far away. Okay. So here we have something like n to the log n, where the log n is raised to a power like 1 over 2 to the delta. So it's a quasi-polynomial lower bound, and it degrades very badly as delta increases. It stops at depth like log n. So the lower bounds are much weaker, and they're also much more recent. The lower bounds for Boolean constant depth circuits we've known since the 80s. Here, we only had super polynomial lower bounds for constant depth circuits 3 years ago. So this was a very big, open question in the area. And there's a wonderful paper by Nutan Lamaya, Shrikant Srinivasan, and Sebastian Tavana, where they proved super polynomial lower bounds. And as an application of existing hardness randomness machinery, they got some kind of a generator. So their generator, it has seed length n to the epsilon. You should think of epsilon as a small constant, like 1 over a million, or even something slightly subconstant. The degree is small, it's like log n over log n. But the complexity of this generator is it's very tightly coupled to the circuit you're trying to hit. If you're trying to hit a circuit of depth delta and size polynomial, well, this generator, it's going to correspond to evaluations of some polynomial that's hard for these parameters, right? So you'll end up evaluating, it's a Nissan-Wigderson type generator. So you end up evaluating a polynomial that requires depth delta and polynomial size where this polynomial is slightly larger than this polynomial. There's some coupling of the complexity here. So you get a generator, and this is perfectly fine for derandomization. But the complexity of the generator, it's always coupled to the complexity of the object you're hitting, and the generator always is a little more complicated to evaluate than the circuit you're trying to test. Okay. So there was some improvement on this. So in some later work, myself and Michael Forbes, we designed a different generator that gets the same seed length, n to the epsilon, but the other parameters are better. Now the degree is just something like 1 over epsilon. So if epsilon is a constant, this is a constant. And then what I really liked about this is the complexity of the generator is now decoupled from the object you're testing. So this generator you can compute in near linear size and depth which is like log 1 over epsilon. So now if you're trying to hit something of depth, say 1,000,000, this might only have depth 10 or depth 20. And you still get something interesting.
So for the first generator doesn't give you a lower bound, no? Because its size of the generator is now larger than the circuit it competes with.
So it still gives you a lower bound,
Okay.
but it doesn't, the lower bound it gives you is, it's about the same quality of lower bound that these people just proved with their bare hands.
But how can it give you that lower bound? Because you are creating a circuit which is larger than what you want to fall. And that's not a problem.
That's not a problem. Because what you care about is you have a theorem just sitting in the sky that tells you anything that breaks this generator. If I have a non-zero polynomial that becomes 0 when you compose it with this generator, well, that polynomial must require large circuits. Right? So now you take this generator, someone gives it to you, and you can do some linear algebra and find a polynomial that breaks the generator. So that's how you prove your lower bound. You lose out a little bit maybe on the explicitness of that hard polynomial, actually. But typically, I don't know of an instance where we prove a new lower bound by designing a generator. I think it's always in the other direction. So this is kind of the state of the art for constant depth circuits is, you can decouple the complexity of the generator and the thing you're hitting, but this is still somewhat large. Can you improve this more? And that's what I want to tell you about today. So in what I'm going to tell you about, you can get much better complexity for the generator. You can compute each output of the generator with a formula of size 3, so constant size formula. The generator has degree 2, all the outputs are quadratic, but you lose out a lot in the seed length. Now the seed length is basically n, but it's minus some n to the power 1 minus epsilon. So it's a non-trivial seed length. Like there's actual content in this theorem, but this is not useful for derandomization. Right? It's just interesting as a construction that, you can actually get these very efficiently computable generators that do something non-trivially pseudorandom. Okay, so I want to tell you more concretely, what is the statement that's underlying this generator, and then maybe give you some idea what the generator looks like and even why it should be correct. Okay, so here's the theorem statement. So there's some explicit generator. It has seed length n minus n to the 0.99, so like pretty close to n. This seed length is not great, but the other parameters are great, which is, it gets degree 2. You can't do anything interesting with a degree 1 generator. This is basically just some change of coordinates in the polynomial. So degree 2 is the best you could hope for. And it's computable by constant size circuits. And families of polynomials that are computable by constant size circuits, this is some complexity class called VNC0. It's just algebraic NC0. So that's the VNC0 in the title. So there's this generator, and it hits polynomial size. Well, we can fill this in 3 different ways. So the first statement is that it just hits constant depth circuits of polynomial size unconditionally. No assumptions here, no anything. You can also make this generator hit polynomial size formulas, but you need a hardness assumption. And the hardness assumption here is that the determinant should require formulas of super polynomial size. Now I want to mention this is a pretty strong hardness assumption because we know the determinant can be computed by formulas of size n to the log n, quasi-polynomial size. So this is some very tight lower bound assumption that you can get the determinant in quasi-polynomial size as a formula, but not in polynomial size. It's a believable assumption, but it seems like it would be hard to prove. Anyway, so we can hit formulas. And the third result is that you can actually make this generator hit what are called algebraic branching programs. If you don't know what these are, there's something intermediate between formulas and circuits. And again, you need a hardness assumption. You need some separation of complexity classes. So this VBP thing, this is polynomials that have small branching programs. And this VP, this is polynomials with small circuits. So this assumption is saying there's a family of polynomials computable by small circuits that cannot be computed by small branching programs. Again, this is a very tight separation of complexity classes. Not clear if this is actually true or not. I've talked to some people, some very reasonable people have told me they think this is the false, that these two classes are the same. But
because of the V part, or even do you think branching programs and circuits in P are the same?
yeah, so in fact, every circuit can be transformed into a branching program of quasi-polynomial size. So this is again like a polynomial versus quasi-polynomial question. And like when I told Avi about this, he's like, well, I just don't think this is true. And like, Avi tells me something, I believe it.
No, sorry, I think my question,
Yeah.
do the same people also think this is not true in the Boolean world?
No, so one thing that's going on here is in the algebraic world, you have these very strong depth reduction results. If you have a polynomial sized circuit, it's basically log squared depth. You can reduce it to log squared depth with very small polynomial size blow up. So this is like in algebra, we have a theorem that says P equals NC2.
Okay.
So there's very strong, depth reduction going on here. Yeah. Okay. So this is the statement of, the generator construction, well, at least what you get. And what I want to focus on today is just hitting constant depth circuits. Because here I don't need hardness assumptions, I don't need new definitions, we can just try to do this with our bare hands and see what happens. So any more questions before I move on? Okay, so I want to talk a little bit about, how would you, like say you have a generator, someone comes up to you on the street and is like, hey, here's a generator, I think it works. How would you try to prove or disprove this? Well, it turns out the right thing to look at is the set of polynomials that break the generator, right? And we can give this thing a name. So I want to give this a name and say that these are the right things to look at. So I'm going to define an object called the annihilator ideal of a generator. Okay, and if you know what an ideal is, that's great. If you don't, just zone out when you read that word. So we have a generator.
Is the ring theoretic ideal?
Yes.
Okay.
So say you have a generator that takes L numbers to N, like L random complex numbers to N pseudorandom complex numbers. I'm going to look at the annihilator ideal, which is the set of all n-variate polynomials that become 0 when you compose with the generator. An ideal means that the set is closed under addition. If f and g both, like if f and h satisfy this condition, then f plus h does. And if f satisfies this condition, then f times h for any h also satisfies this condition. So I want to look at these polynomials. These are the things that break the generator, that make it not work. We want to understand these. And maybe just one comment is that this is a feature of algebraic pseudorandomness that I really like. You can actually hope to describe exactly what this set is. And that's not something that Boolean pseudorandomness, I tell you I have an epsilon bias space or like ky is independence or some combination of these, and I ask, well, when does this fail? You don't always have a clean answer. Here you can get extremely clean, clear answers as to why your generator fails. So here's a lemma. So suppose I, again, have a class curly C that I'd like to test. So you should think curly C, these are polynomials that have small low depth circuits. Well, if you unpack the definitions and you look at what it means for G to hit curly C, this is exactly saying that if you look at the intersection of the annihilator with curly C, only the 0 polynomial lives here. This is just rephrasing definitions. So if I want to prove that G hits curly C, I'm going to prove that the only thing in this intersection is 0. Now, what does it mean? Well, how would I prove that the only thing in this intersection is 0? Take some non-zero element of the annihilator. I want to prove that it's outside curly C. That is a circuit lower bound statement. I want to say that every annihilator requires large complexity to compute. That's going to be our goal. So the point here is I want you to be in this frame of mind that to prove a generator is correct, it's entirely equivalent and turns out to be convenient to show circuit lower bounds for the annihilator. And like I said, we can actually hope to understand precisely what this is. And that makes this whole machinery go through. Okay, so let's warm up. I want to hit depth 3 circuits. So it's a circuit that's a sum of products of sums. The circuit has polynomial size, and I want to hit it with seed length n-1. Okay, most like basic task, just get non-trivial seed length. I don't really care about the complexity of the generator. It should be, say, computable by polynomial size circuits, but that's it. So how would you get a generator with stretch 1? Well, in the Boolean setting, what you would do is you would just take your, say, n-1 random bits, and you would concatenate the evaluation of a hard function on those bits. So let's do something like that. Here's an idea. Let's set our generator to take n-1 inputs. It just spits out those numbers, and then it also spits out the evaluation of some polynomial f on those numbers, where f is a hard function. F is some polynomial that requires large depth 3 circuits. Okay, it seems like if you want to break this, say you want to distinguish this, which is maybe some pseudorandom thing from something truly random, you need to compute something related to f. Now, it turns out you can characterize exactly what polynomials break this. So say I have some polynomial h, which when I plug in the generator, simplifies to 0. Well, you do some algebra, and you can prove that this happens exactly when y minus f is a factor of h, where I've got these n-1 x variables, and the nth variable is this y. Right? These are exactly the polynomials that break this generator. So now what we need to do is, if we want to make this generator work, we should choose f, not only so that f itself is hard, but in fact, any multiple of y minus f is also hard. Okay, this is maybe, if you want to think of it as like an average case lower bound, that might be a useful perspective to have. Okay, so let's rework this idea. We want to pick f where multiples of y minus f require large depth 3 circuits. And now you go down the street to the circuit lower bound store and you pick something up off the shelf that tells you the determinant is going to work for this. You can show it's, don't ask me how, I can tell you later, it's not straightforward, but multiples of y minus the determinant actually require large depth 3 circuits. Okay? And this is using some special properties of the determinant. We don't know if this is true in general. That if a polynomial requires large depth 3 circuits, then also its multiples require large depth 3 circuits. Not clear if that's true in general. So let's take this idea, throw the theorem into it, and we get a generator with 1 bit of stretch. That you can take these n-1 variables, concatenate them with the determinant, and you hit depth 3 circuits of polynomial size. So we have a generator. It has non-trivial seed length, and it hits depth 3 circuits. What's the problem? The problem is, of course, this thing is way too expensive to compute. Right? I know lower bounds against the determinant for depth 3 circuits. So it seems like I'm just doing something that's useless. How is this going to give me a very low complexity generator? So that's the big question, is how can you take this generator and just improve its complexity to be something much, much smaller? And the idea is we're going to replace the determinant itself by a collection of polynomials that encode a computation of the determinant. Okay, so I want to leave the determinant behind for a little bit, and I want to illustrate the idea with an example. Okay, so here's the example. We're bringing back this circuit from the second slide. So you should think of this as our hard polynomial. Okay, x1 squared minus x2 squared. Of course, it's not hard. Here's a small circuit, but imagine this was the determinant. I just don't want to draw the circuit for the determinant. So I've numbered the gates here, 1, 2, and 3. And what I'm going to do is I'm going to come up with some kind of, I needed to come up with a name for this. I'll call it a local encoding of this circuit. Some sort of Cook-Levin style encoding. So here's the generator I'll build from this circuit. the generator will take 5 inputs. So you have 2 inputs, which correspond to the inputs of the circuit. And you have 3 inputs, which correspond to the gates of the circuit. The generator has 5 inputs. I'll produce 6 outputs. So the first 2 outputs are just x1 and x2. Now I want to encode some kind of statement that says the circuit is computing correctly. So here's how I'm going to do that. I'm going to write down as the third output y1 minus the sum x1 plus x2. And whenever I'm writing down these polynomials, you should think implicitly there's an equals 0 attached to every polynomial. So really what I'm trying to write is the equation y1 equals x1 plus x2. But for reasons I have to write it this way. There's always an equals 0 implied. That's how you should read this. So this says that the first gate is computing correctly. Then we also say, okay, the second gate is computing correctly. It should be computing x1 minus x2. And then I want to say the third gate is computing correctly, that y3 is computing y1 times y2. And then I'll just throw y3 on the end. That's the output of the circuit. Okay? So it's clear that all of these guys, I mean, they're very low complexity polynomials. But like, what can this possibly do? Right? This seems like such a, I don't know, how would you even prove that something like this is pseudorandom? So I'm going to erase the circuit, move the generator to the left side of the slide, and let's ask this question. How would you annihilate this generator? Right? We want to understand the annihilators in order to prove some kind of pseudorandomness property. So how would you annihilate this thing? And one way you can do this is you can try to trace the circuit gate by gate and simulate its evaluation. Okay? And again, I just want to mention, I'm going to show you how to annihilate this. And if you're getting lost in the sea of algebra, just remember, there's always an implied equals 0 on the right-hand side of a polynomial. So you should really think of these as equations, not as polynomials. But, okay, I have to write everything as polynomials. Okay, so how do we annihilate this? What's our goal? We want to find a non-zero polynomial h in these z variables. There's 1, 2, 3, 4, 5, 6, corresponding to the 6 outputs of the generator, so that h becomes 0 on this substitution, right? These are the polynomials the generator is outputting. So what could you do? Well, let's try to argue that the that the circuit is computing correctly. So for example, x1, well, again, think of this as x1 equals 0. x2 equals 0, and then y1 equals x1 plus x2. Now we as humans know that if x1 is 0 and x2 is 0 and y1 is their sum, then y1 is 0. So let's try to take some combination of these 3 guys that will give us y1 on this substitution.
Sorry, I'm a bit confused as to what the seed length is going to become now.
So the seed length is 5.
But we're only working with starting out with just x1 and x2. Oh,
sorry. So the seed length is 5. It's these 5 variables.
Okay.
x1, x2, y1, y2, y3. And it outputs 6 polynomials. So we're going from 5 inputs to 6 outputs.
So we're not working with the n-1 perspective that we had earlier, or is that still?
Kind of. So the n-1 thing was saying, here's how you get 1 bit of stretch. This is way too complicated.
Yes, okay.
So I'm going to massage this, and now we're going to do something that makes this thing much, much lower complexity and still goes 1 bit of stretch.
Okay.
If you're not seeing a way to glue these 2 things together, don't worry about it.
All right.
Just let's go with this for now. Okay, so again, there's always an implied equals 0. x1 is 0, x2 is 0, and y1 equals x1 plus x2. As humans, we know that this means y1 is 0. I want to just write down some algebra that captures this reasoning. So if you write down the polynomial, well, z3 plus z1 plus z2, when you perform this substitution, this guy simplifies to y1. You can do the same thing with y2. If you look at the polynomial z4 plus the difference z1 minus z2, on this substitution, it simplifies to y2. This should be relatively easy to see so far. Now, okay, we know sort of in our, we've got something that says y1 is 0 and y2 is 0. And now we also know that y3 equals y1 times y2. So we should in some way be able to write down that y3 is 0. How are we going to do this? Well, let's take z5 and add to it the product of these two guys. What happens when you do the substitution? Well, this guy becomes y1, this guy becomes y2, so you get y3 minus y1, y2, plus y1 times y2. Well, the whole thing simplifies to y3. And now we're home free, because if you look at z6 minus this, how does it behave on this substitution? Well, z6 becomes y3, and so does this. So it becomes 0. Okay, so what did we do? We somehow traced the execution of the circuit, and we got an annihilator. And what I want to argue is that you have to do this. That if the circuit is complicated, even though these encodings themselves are very simple, to annihilate it, you would have to simulate this really big circuit that they're describing. So let me give you some idea of what's going on here. So like, what is this annihilator? It's a, yeah.
A bit confused about the input x1, x2. Like you want
Yeah.
to, like why not ensure that x1 is equal to 0, x2 is equal to 0? That's not, you're like restricting the input, right?
Right, so there's no restriction of the input going on here. I'm just trying to say that, like, how did I find these polynomials? I'm thinking of reasoning about polynomial equations. If the equals 0 thing doesn't make sense, don't worry about it. Just believe me that you do these substitutions, you get something that breaks the generator. And we did something that simulated the circuit. Okay, so like, what does this thing look like? So there's a magical tool called a computer. You can feed this into it, and it'll expand out the polynomial for you, right? And what I want to point out here is, it's doing something interesting. It's saying, you have this z6, which was the thing that corresponds to the output part of the encoding, minus, z1 squared minus z2 squared. This was the polynomial that the circuit computed. And then there are some extra terms, and you should think of these as junk. And why should you think of these as junk? Well, every one of these terms has a z3, a z4, or a z5 in them. And so if I set z3, 4, and 5 all to 0, this thing collapses just to variable minus hard polynomial, which was the sort of thing that we saw earlier. Okay, so this was like one really complicated example, and you would ask, like, hey, are there other annihilators? Like, sure, this thing is basically simulating the circuit, but maybe there's some other more clever thing you could do to break this kind of generator. And it turns out you can't. This is the magic of algebra. Every annihilator of this, very particular seed length 5 generator I showed you, every annihilator is a multiple of this one. So there's a lot of nice structure here that you can understand that you don't always have in the Boolean setting. And if you care about the proof, it says something about transcendence degree. It uses the fact that this polynomial is irreducible. But I don't think you all want to sit through algebra class more than what this talk already is. Okay, so let me just say a little bit more generally, like, what is this thing doing? So what is this local encoding doing? So you're given some n-variate circuit C, it has size S, and what you're going to do is you're going to build a map that stretches n plus s inputs into n plus s plus 1 outputs. Okay, and what do? Well, the inputs, you have n variables that correspond to the inputs of this circuit, and you have s variables that correspond to the gates of the circuit. Now the first n outputs of the generator are just these n input variables. Right? Then the next s outputs of the generator, they're these sort of local equations that say I take gate, the variable for gate I, and I subtract from it, the variable for its left child, plus times whatever the variable for its right child, right? I have all these polynomials that encode local correctness of the circuit. And then the very last output is just the variable corresponding to the output gate of the circuit. Okay, so let's observe, like, this might be an interesting generator. What kind of parameters do we get from it, right? So if G is a local encoding of a circuit, well, for one, this generator would have non-trivial seed length, right? It gets a stretch of 1. And it turns out getting stretch 1 is enough for the parameters I claimed earlier. It has degree 2, right? Every output was just some either degree 1 or degree 2 function of the inputs. And here's the thing we wanted. Each output can be computed by a circuit of size 3. That's this VNC 0 thing. Okay, so now the question is, like, we have this candidate generator. Can we understand its annihilators? And I worked through this, we worked through this example of this, sort of size 3 circuit, and we understood that the annihilator looks like you're simulating the circuit gate by gate. That's true in general. There was nothing special about that example other than the fact that I could write it on the slide. So, here's the main lemma that you can prove. I'm not going to actually say anything about the proof because it's just going to get dry. But here's the lemma. So if you take the local encoding of some circuit that computes a polynomial f, then every annihilator is a multiple of this thing. So you have z n plus s plus 1. This is the variable that gets the output of the circuit, right? In the local encoding, there was just this very last output that corresponds to, like, the top gate of the circuit. That's what this variable gets, minus f on the first n variables, plus some error term g, where the monomials in G, they all depend on these sort of intermediate variables. And so you should think that if I set these guys to 0, G drops out, and I just have this, which looks like the sort of thing we could reason about earlier, right? I told you that variable minus determinant is going to have hard multiples. So maybe you can sort of patch this into the thing with the determinant. So that's what we're going to do. So let me just...
I have a question. Can you hear me?
Yes, yes, yes.
Okay, great. The question's about the fan-in. So if the multiplication gates have high fan-in, then you're not going to have the degree you want, right? It's not going to just be degree 2.
Right.
And if all the gates have fan-in 2, then you're not going to be able to take with the depth 3 in the example of sigma pi sigma, for example.
Yeah.
You can only have 8 inputs or whatever, right?
Right.
So what's going on?
Yeah, what's going on? So here it's actually okay that, so if the circuit has very large fan-in, let me rewire the circuit so that it always has fan-in 2. This might blow up the depth of the circuit, but you still get this local encoding that only has degree 2.
Okay.
And in terms of the pseudorandom properties of the generator, that massaging is not going to affect the pseudorandomness.
Okay, thanks.
Yeah. Okay. So this is something you can prove. I don't want to prove it here. Let me just show you how you can use this to build a generator. Okay, so here's the main theorem, is that if you take the local encoding of a small circuit that computes the determinant, then this will hit depth 3, in fact, constant depth circuits of polynomial size. And here's roughly how the proof goes. Okay, so 1, we know that any annihilator of this generator is going to be a multiple of this polynomial here. Okay, now I claim that if you had a small circuit that computes some annihilator, you can massage that circuit to remove this G term. Okay, the idea is you would want to set just the intermediate Z variables to 0. This would kill G, but it might actually set your annihilator to 0. So you need to do something more careful, but this is some completely standard thing in arithmetic circuit complexity. And And then you just say that, well, you know, if you had a small circuit for the annihilator and you get this small circuit for a multiple of the determinant, you've reached a contradiction. Because we know that every multiple of the determinant requires constant depth circuits of very large size. So this is roughly how you would prove that, you know, you take this local encoding of a circuit for determinant, this hits polynomial size constant depth circuits. And, you know, this same kind of construction, if you replace determinant with other functions, you can get other pseudorandomness properties, but you have to make some kind of hardness assumption. Okay, so, you know, I wanted to say something about proof complexity, but I think I'm running low on time. So let me just wrap up.
Robert,
Yeah.
one thing. So for getting
Let me go
the
back.
stretch you wanted,
Uh-huh,
then you're just going to block these things next to each other and you apply it.
yes.
Good. And then if you could have proved an exponential lower bound, you could have even get n over log n-ish type stretch. Like, why do you want to have n to the 1 minus epsilon? I guess because you want your blocks to have size n to the epsilon.
Yes,
Which a polynomial lower bound in n to the epsilon is a still polynomial in n.
yes, 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 yes. So I think, yeah, you could make that, yes, so you're subtracting this n to the power 1 minus epsilon. You can make the thing you're subtracting larger as you get better lower bounds. Yes, so if you had,
Even in the ultimate case, your less stretch will be like n over log n or something. You can have more than log n.
I think, yes, 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 yes. So as far as the stretch goes, this, I mean, it's really not giving you much, even in the, assuming these best case lower bounds. Yeah.
And that might be tight if you want some very good, like low dp simple generator.
Yeah, yeah. So let me just, yeah, let me say that I don't know. And I think that would be a really great question. So I'll just say that that's open question number 2, essentially, is can you design generators that are this simple, but get better parameters? So could you get, you know, seed length, which is like 0.99 times n? Or, you know, can you show me some kind of trade-off that if you're aiming for this really low complexity, like there's some lower bound on the seed length you can expect to get? I don't really know how to prove these trade-offs, but I would be really interested in anything interesting. Of course, I think the main open question here is, can you find a reasonable assumption that you can use to design a generator that has every output computable by a constant size circuit, and the generator also hits polynomial size circuits? You know, because we're using these local encodings to build the generator, we're sort of stuck that, you know, we have to, whatever hard function we're using to power the generator, it has to have a small circuit to begin with. So we just can't, you know, this idea doesn't seem to extend to circuits. So I think that would be really interesting. And then, you know, there's some connection to proof complexity where you get some lower bounds for a subsystem of this thing called the ideal proof system, just as a direct consequence of the generator. But it's for some restricted subsystem. Can you improve those to just the full, like, yeah, remove whatever that restriction is? Anyways, that's all I wanted to say. So thanks so much for your time.